Morning, everyone. Is the video all right? I played with it this morning, and I feel that I have put it at a wrong angle. How's it looking? Looking all right? Not too distorted? Thank you. Morning, everyone. Very good. How's everybody doing? Questions while we wait a few moments for everybody to come in? Morning, everyone. How large is the screen that you read the chat off of? It's about, I would say, a third of my screen. Tutorial 9 should be part. It's tutorial 11 that we're having an issue finding a TA for. We might have to cancel that one. You can attend a different tutorial if your Monday's tutorial was canceled. It's fine. The tutorial questions are posted in my courses. Yeah, for this week's content, that's right. You can attend any of the tutorials you want, absolutely. Tutorial links should be on my courses in the content section. You have to access web work through the link given on my courses. I'm going to have a look with respect to tutorial 9, see what's going on there. You didn't see a tutorial 14 as well? It really should only be 11. 11 was the issue. All the other ones should be there. You don't have to stay with the same tutorial. You can move around. It's all good. My area of mathematics is the proofs of calculus. It's called analysis. Well, I mean, it starts off being the proofs of calculus, and then you do more and more and more, so it builds up. But that's my area. No, all the tutorials should be there except for tutorial 11. I'll email the TAs, see what's going on there. Everything should be up. It is the first week. Not everybody's up to speed, so let's give them the benefit of the doubt. But to be honest, I've been so swamped with work, I haven't even been able to check that the TAs have posted everything. But I'm gonna get right on that. Tutorial schedule should be, well, first of all, you can always see the tutorial schedule on Minerva. And I had asked the TAs to post the link, their links to Zoom or whatever they're using in the content section on my courses. Do you do the tutorial questions before the tutorial or during? I mean, it's up to you. If you want to do them before, you can certainly do that. You should have a little bit of time to do it during the tutorial. Very little, though. So it's best if you did it beforehand. But of course, if you do it beforehand and you're comfortable with your answers, then there's really no, is there a point in going to the tutorial? It's a valid question. You can attend any tutorial you want, that's fine. All right. Yeah, Joanna, there seems to be an issue with the grading. I don't know what's going on there. Like I said, WebWork has been revamped. Normally, you would get your mark immediately. I've emailed the resident expert on WebWork. I'm waiting for an answer. Fresca is a drop-in tutorial. And sorry, it's a drop-in center where you go and you ask questions. The tutorials are structured where the TAs are going to do those questions that have been posted. I mean, of course, you can always ask questions in the tutorial, but yeah, Fresca is really where you want to ask questions. Let me say, Fresca, there's not going to be any specific questions assigned to them. It's a drop-in center where you ask your questions. I mean, the WebWork 0 is not counted, but I would have expected it to be graded nonetheless, just not counted towards any mark. Yeah, I don't know. Look. Tutorials, apparently not all tutorials are up. You access WebWork through My Courses. The exams are hard. All right, that's enough. That's enough. Let's get to work. Let's get to work by going back to what we were doing last time. We were looking at inverse functions. We defined what it means for a function to be injective or one-to-one. Let's consider this. Verify that the function is injective, and find the inverse. And find the inverse if it is. Noah's asking, how is WebWork to be handed in? You answer the questions directly on the computer. Now, perhaps you downloaded the PDF, and now you're wondering how that's going to work. Nothing wrong with downloading the PDF. However, that's not how you're going to answer the question. Instead of downloading the PDF, click on every individual question, and there'll be space for you to type in your answer, and that's how you submit the WebWork. You get unlimited attempts. All right. Here it is. Verify that the function is injective and find its inverse if it is. So, I mean, it's not even clear that this function is injective. Perhaps it's not. X to the 4 minus 16. Oh, it doesn't matter. Thank you, though. But interestingly enough, it makes no difference here because f of 1 is minus 15 And f of negative 1 is minus 15 again. So in other words, not injective. Not injective, and that's it. Not injective, this function does not have an inverse. Can we take pictures of the WebWork answers and paste it under each question? Well, you're referring to what you're going to do in CrowdMark. WebWork, it's much easier than that. You type in your answer in this space provided, that's it. And it gives you instant feedback. So there's no marking, there's nothing, but at the same time, there's no part marks for showing your work. Are there certain types of equations, quadratics, and so on, where one can assume they are not injective? Well, let's not assume anything. Is there an algorithmic approach to determine whether a function is injective? If you have the graph, we have this nice horizontal line test. So that's kind of nice. Do we have long answers during exams? You only have long answers. No multiple choice questions. All right, consider this. Ali was asking, what is the point of knowing whether a function is injective or not? And as Maddie suggested, a function is invertible if and only if it is injective. Let's verify that this function is injective. And you know how to do that. If you start off with g of a equals g of b, here cube root of a is going to be cube root of b. We're going to cube both sides. If you do the same to both sides, equality is maintained. And the cube root cubed is just a. Cube root of b cubed is just b, and there you have it. We assumed g of a was equal to g of b, and we concluded a is equal to b. So this function is 1-to-1. Jenny's asking, no, April is asking, if we do this method for number 10, don't we get that the function is 1-to-1? The problem is when you start taking the fourth root, that's the issue. It could be positive or negative, as this counter example shows. So it's not going to work anymore. This function is 1-to-1, so it has an inverse. To find the inverse, you know what to do. We interchange x and y. And you solve for y. We're going to cube both sides. And we get that y is x cubed. So if g of x is this, then g inverse is x cubed. You know you can check. You know you can check, right? Because when you take the composition, This is g of x cubed. And everywhere you see an x in here, you replace with x cubed. So this is x cubed to the 1/3, which is just x. And I'll let you do the other one as well, but there it is. How are we doing? Olivia is asking, how can we tell which method to use? The one on the left or the one on the right? Well, how can we tell which method to use? Experience. Experience. After having done so many, you sort of have an idea of whether the function is going to be 1-to-1 or not. Here we had x to the 4 minus 16. You know what that graph looks like. You know what x to the 4 looks like. So x to the 4 minus 16 is going to look something like this. And there you have it. It's not 1-to-1. Here, cube root, you kind of know what the graph looks like. Consider this. Well, I mean, I'm reading the comments here, and people are saying any function with an even exponent is not going to have an inverse. And then we have this counterexample. Exactly that. Amelia has fixed it because you have to look, well, not the range, but rather the domain. The domain. Exactly. Right? First of all, why don't we talk about this function before finding its inverse? Let's graph this function. You know how to graph this, right? What kind of function is this? It's a quadratic function. So you know that it either opens up like this or opens down, depending on the coefficient of x squared. Here the coefficient is positive, so it's going to open up. Let's find the vertex. The x-coordinate of the vertex, negative b over 2a. So this is 2 over 2, which is 1. The x-coordinate of the vertex is 1. And when x is 1, y is negative 1. And that's all you need to graph roughly the function. Vertex, when x is 1, y is negative 1. So this is the vertex, and it's going to open up. It's nice to label the x and y intercepts. And as Nandini suggested, if you factor out an x from here, It's easy to see that that y is 0 when x is 0 or 2. So we have x-intercepts at 0 and 2. And there it is. This is the graph. Now, obviously, not one-to-one. Right? Now that we have the graph, it's easy to see that it's not one-to-one. However, the domain restricts our graph to the right half. Right? So this is the only half we're interested in. And now this is one-to-one, right? Any horizontal line crosses at most once. So now it's one-to-one, even though they didn't need us to prove it. Now we understand why this restriction makes it so. Very well. Now let's prove, let's find the inverse. The question was asking us to find the inverse. How did you get both intercepts again? We factor, and the intercepts is when this is equal to 0. So now we have a product equal to 0. And the only time that happens is if one of the factors is 0. So x is 0 or x minus 2 is 0. The restrictions on the domain carry over to the inverse. They do, absolutely. In some form. In some form. We're going to discuss that momentarily, absolutely, Joanna. But where were we going with that? We were looking for the inverse. So to find the inverse, we had y is x squared minus 2x. We interchange x and y. You know how to do that. Right? So x equals y squared minus 2y. And solve for y. Rudy is asking for materials similar to the exam. Well, I mean, it's difficult to discuss that because we haven't written the exam. What I suggested was do all the odd problems. That should be enough. Jennifer, very nice. We're going to use the quadratic formula to solve for y. Bring the x to the other side. And now you have a quadratic in y. Very nice observation. Very nice observation. So you can use the quadratic formula. Very nice. So let's recall. Well, y is negative b plus or minus square root of b squared minus 4ac over 2a, where ay squared plus by plus c is equal to 0. And that's exactly what we have here. So in this case, y is 2 plus or minus, right? A is 1, B is -2, C is -x. So 2 plus or minus square root of b squared minus 4ac all over 2a. Let's simplify that a bit. 2 plus or minus square root of 4 plus 4x. Let's factor out a 4 from here. And now the square root of a product is the product of the square roots. Square root of 4 is, of course, 2. I don't want to erase that. So that is 2 square root of 1 plus x over 2. If you factor out a 2 from the numerator, 1 plus or minus square root of 1 plus x over 2. These cancel out, leaving you with 1 plus or minus the square root of 1 plus x. Why aren't you using the coefficient of c? You are. C, in this case, is -x. But now, of course, you understand that there's an issue. Right? There's an issue here. What's the issue? You've got a plus or minus. It's 1 plus or minus square root of 1 minus x. 1 plus x. There's seemingly two values. And there isn't. Was it frozen? No, let's wait. Are we back? Good. Right now, there's this thing. There's this plus or minus, which is not a function. Well, it was important to use a quadratic formula, and we did so, absolutely. But now it brings us to the interesting thing that we have a plus or minus here. And now we have to decide if it's the plus or if it's the minus. And that's where originally the restriction to x being bigger than 1 comes into play. Right? For values bigger than 1. Because really, we artificially restricted our attention to this half, but it could have just as easily have been that half. Because this half is 1-to-1 as well. So that part has an inverse as well. So now which corresponds to which? The positive is going to correspond to the right-hand side. The positive is what we want in this case. Right? Because the domain of this function should correspond to the range of this. And here we wanted values bigger than 1, so we have to take the positive in order for this to be values bigger than 1. Exactly right, Shamir. So let's put all of this together. What are we saying? if f of x is x squared minus 2x for x bigger than 1, then the inverse is 1 plus square root of 1 plus x. And why don't we take a moment to check here. When you take the composition, let's see what happens. This is f of 1 plus square root of 1 plus x. So everywhere you see an x in your function f, you replace with this. So this is 1 plus square root of 1 plus x all squared minus 2 square root of 1 plus minus 2 times 1 plus square root of 1 plus x. Let's simplify this, see what happens. You know what we're expecting to happen, right? The composition should give us x. What does it really give us? You're squaring this, right? So that squared, this times 2. Plus that thing squared. And let's distribute the negative 2. Minus 2 minus 2 square root of 1 plus x. These things cancel out nicely. And then you're left with 2 plus x minus 2, which is easily seen to be x. I'll let you work out the other case. The composition of f with its inverse the other way. Could we explain the plus minus once again? I claim, right, here we were restricting our attention to x bigger than 1. The domain of the function was x bigger than 1, which corresponds to the range. So this is domain of f. And the range of its inverse. Right? Because how do you find the inverse? You interchange the x and the y. So the domain becomes the range, and the range becomes the domain. So the range must be bigger than or equal to 1. This is the range. So if you took the minus, it's 1 minus stuff. That would have been less than 1. But of course, if you were restricting your attention to the other half, then you would have taken the minus. So the plus or the minus is very important, and you have to know which one you're working with. And that's all due to the restriction of the domain to begin with. Our function itself, this, on the whole real line, did not have an inverse because it was not 1 to 1, but by restricting it, you make it 1 to 1, and then it has an inverse. 2 square root of x plus 1, I mean, we have a positive 1 here and then a negative 1 there. So they add to 0. How are we doing here? Questions? Anybody? Do we want to do one more? Or are we good with this? Moving on. One more? Let's do one more. Let's do one more, and then we'll do a few more later on. We'll come back to this. Same question. We're assuming 1-to-1. It's only asking us to find the inverse. So y equals this. Interchange x and y. And solve for y. Let's cross multiply. Expand. Sorry, Michael, I haven't seen your question. Should we restrict the domain of the inverse? Otherwise, you might get negative negative square roots and imaginary results. Absolutely, absolutely. The domain of the inverse was the range of the original function. So the range went from -1 to infinity. And in that way, I mean, I've conveniently rubbed it off now, but -1 to infinity was the domain for the inverse. Thank you. Expand. Let's bring all the y's to one side. Everything else to the other. Factor out a y. And so y is 6 minus 7x over 5x plus 3. That is the inverse. Very nice. I'll let you check here, right? I'll let you check that. So this is our H inverse, and I'll let you check that the composition gives you x. Right? It's a nice exercise to do that, because if you do that, you know you're right. And then you don't even have to check the answers in the back of the book. If the composition gives you x both ways, there's no hesitation. That has to be the right answer. And let me say this, sometimes the book makes mistakes. So if you can check that you're right, and this would be of particular use on in-person exams. If you can check, if there's a way for you to check the answer, to know that you're right, you want to do that. And here you can. So a question that has arisen is, what is the relationship between the graph of f and the graph of its inverse? how are the graphs? Let me. Y equals f of x and y equals f inverse of x related, if at all. Right, and Michael has hit the nail on the head there. They are reflected over y equals x. Right, think about how you find the inverse. You have y equals your function, and then you interchange x and y. So what are you really doing? You're interchanging the x and the y-axis. If you have some graph, well, I mean, let's take the graph y equals 2 to the x. Right? This is the x-axis here, and this is the y-axis. What we're doing is we are interchanging the x and the y-axis when you're solving for the inverse. So it's going to be the same graph, but with the axes interchanged. Right? So for large negative values of x, the function is close to 0. For large negative values of x, the function is close to 0. There it is. This is the graph of the inverse. You're just looking at it from the side, if you will. Sort of I don't want to try to explain how I look at it. It's going to confuse you more than anything else. But you're essentially just switching the x and the y-axes. Or, as Michael suggests, it's really a reflection about the line y equals x. If you took the mirror image, that's what you would get. There it is. So that's how a function and its inverse are related, which brings us to where we left off last time. And really the point of this whole discussion about inverse functions was the inverse of the exponential. Right? Y equals 2 to the x is an injective function, so it has an inverse. But if you interchange x and y, there's no way for you to solve for y. But we know it has an inverse. So if f of x equals 2 to the x, its inverse exists, and we give it a name. And as Jennifer points out, we call it the logarithm. And this is true for any exponential function in general. If you have an exponential function, a to the x, where a is bigger than 0, not equal to 1, then the inverse must exist, because you know the graph, and the inverse, we give it a name, and we call it the logarithm. So logarithm base a is the inverse function to the exponential. And since you're very familiar with the exponential function, then of course You're comfortable with the logarithm because they are just inverse functions of each other. Right? Example, if your function is 2 to the x, you know that f of 3, 2 cubed is 8. F of -1 is 1/2, and so on. The inverse function is the logarithm, which means that if you plug 8 in, you need to get 3 back. If you plug 1/2 in, you need to get -1 back, and so on and so on. The logarithm is the inverse function to the exponential. By knowing how the exponential works, you know how the logarithm works. And properties of exponentials translate into properties of the logarithm. Let's consider a few properties. So again, if your function is a to the x, its inverse is the logarithm base a. What is, regardless of what a is, what is f of 0? What is a to the 0? A to the 0, of course, is 1. Thank you, Jenny. And consequently, when you plug 1 in, regardless of what a is, you have to get 0 back. Log of 1 is 0. That's because you know that a to the 0 is 1. It's the opposite. It's the inverse function. What else? What is f of 1? A to the 1, regardless of what a is. A to the 1 is a. And consequently, the inverse, when you plug a in, you need to get the 1 back. Log base a of a is 1. Let me give you the few remaining properties without resorting always back to the exponential, but know that you can do that. Logarithm of a product is the sum of the logarithms. Logarithm of a quotient is the difference of the logarithms. The log of a power. You can bring the power down. Those are the 5 main properties. But let me give you one more, which really follows from the fact that exponentials and logarithms are inverse functions of each other. By definition, the composition must be x. But what is this? This is f of, right? I'm using this f here, and its inverse. The composition of the exponential function and its inverse is, right, everywhere you see an x in your function f, you replace with log base a of x. So a to the log base a of x has to be x. April, this is meant to be a review of pre-calculus material. This is stuff you should have seen before. But I mean, even if you haven't, you're seeing it now from scratch. So yeah. So even if you haven't seen this before, you're seeing it now. It's all good. Formula sheet. Well, I mean, look, if this was an in-person exam, and here's the thing. If this was an in-person exam, no formula sheet, no calculator, nothing. So be prepared. You have to be prepared. And this is not an in-person exam, so you're thinking to yourself, well, I mean, I can take it easy. But if in the winter semester we go back to in-person classes, then, I mean, it's going to hit you like a ton of bricks, right? No calculator, no formula sheet, nothing. You have to know everything. The second to last property, which one are we talking about? The power here? Or are we talking about this one? Come on, I'm going to let you take a minute. And while you're answering, let me finish this up by saying the composition the other way, which is f inverse of a to the x, which is log base a of a to the x. That has to be equal to x. Well, that actually follows here from this property right here, right? Because you can take the x down. So you get x log base a of a, and this thing is equal to 1. So in this case, it was easy to see that the composition of f inverse and f gave you x. But the other one isn't immediately clear. But it is of crucial importance because we're going to use this over and over and over again in class. So what I'm saying here, Kamal, is that when you compose f and its inverse, you get x. That's the definition of the inverse function. And what is this? F of f inverse, where this is f and that is f inverse. The proposed f inverse is the logarithm, right? We defined it, we gave it a name. And now everywhere you see an x in your function, a to the x, you replace x with log base a of x. So this is a log base a of x. But this is the composition of a function in its inverse, so that has to be equal to x. By definition. All right. Questions here? How are we doing? How are you doing? Good? Cassidy, you seem to be needing help. Stop me anytime. Let us use these, that last part one more time. And Rudy's asking, will the exam be written as though it is open book? Absolutely. Open book, open internet, open everything. So, yeah. All right, somebody wanted me to go over this one last time. All I'm doing is taking the composition of this function and its inverse. You know by our work on inverse functions last time that the composition of the two must give x. That's all we're using here. All right, let's take a few examples related to this. We are asked to find the exact value is the inverse to the exponential here. It's a logarithm. It's a logarithm with base e, so everything you know about the logarithm applies to the ln as well. So armed with that, we are asked to find exact values what is ln of 1 over e squared. We're just going to apply the properties of the logarithm to evaluate this. Right? This is the logarithm of a fraction. So by this property, this is ln 1 minus ln of e squared. Ln 1, or log base e of 1, by one of the properties I've erased, this is 0. By this property, I can bring the power down, and this is log base e of e. So again, by a property that I've erased, this is 1, and so the whole thing is minus 2. Now that you've committed these to memory, well, let me not erase it. But needless to say, you need to commit these to memory. Ln of root e let's rewrite this root e as e to the 1/2 And again, by this property right here, you can bring the 1/2 down. So this is 1/2 ln of e. Ln of e is 1. And we're done. Let's do one more. Ln of e to the 50. So again, by this property right here, we can bring this power down. So this is ln of e to the 50, ln of e. Ln of e is 1. And now I can apply the same property, bring down the 50. And ln of e is again 1. And there it is. Thank you. Why is ln of e 1? Ln of e, which is really log base e of e, and that's one of the first two properties of the logarithm, right? When the base and the argument are the same. Same question. They are asking us to find the exact value You know what to do. We're going to use this property in reverse. So I'm going to bring that back to a power. This is the same as e to the ln 2 cubed. And now it's gone. It was right here before I erased it. But this is the composition of the exponential and the logarithm. So these cancel out. Right? Since e to the ln x is just x. It's the composition of e to the x and ln x. It's the composition of a function and its inverse. It gives you x. How are we doing here? Same thing? Can we do this in our heads? What's the answer? 1 over 25, thank you, Jenny. 1 over 25. Very good. One more. We can do what? Y is e to the ln x equal to x. If you have a function e to the x, its inverse is ln x, and the composition of a function and its inverse has to be x. But in this case, this is e to the ln x. In our heads, what is that? Who has it? Just 3. Absolutely, Andre. Just 3. Thank you. We are asked to expand as a sum, product, or difference of simpler logarithms. Let's do so. This is, of course, I'm going to rewrite the square root as a power 1/2. Very nice, Zoe. Yep. And now, this allows me to bring the power down. And now the logarithm of a quotient is the difference of the logarithms. So this is ln of 3x minus ln of x minus 3. And now you can take it a step further. You've got a product. So the product, the ln of a product is the sum of the logarithms. And there it is. Right? This is just using properties of logarithms. How are we doing here? Let's do one or two more. All right, so again, so logarithm of a product. So this is the sum of the logarithms. Here, there's nothing else you can do. This is not a product. Don't be confused. Logarithm of a sum does not simplify. Well, I mean, what are we doing here? We're doing stuff from page 64 again. Still that same section we were on last time. I want you to do the rest if you haven't already done it. Right? We're now up to number 44. We'll do one more example, maybe 46. So absolutely. You know, I don't expect you to go further than what we've done, but I certainly would like you to keep up to date. Let's look at this. Cube root, of course, you understand to be x minus 3 squared, the whole thing to the power 1/3. We can simplify the powers here. What happens to the powers? You know what happens, very nice. Well, you say 1.5. Yeah, still section, I want to say 1.5. This is x minus 3 to the multiply, thank you, to the 2/3. And now we can bring the power down. And there it is. Let's do one more. Let's do one more. Question is asking us to express the following as a single logarithm. Will we be doing the inverse of the trig functions? Absolutely. Absolutely. I don't know if we'll get to them on Friday, but certainly we will be doing trig functions on Friday, possibly inverse as well, time permitting. We'll see. What's happening here? We're asked to express as a single logarithm. Let's take this time, right, to bring the powers back up. So this is ln of x minus 2 cubed. So like this. And then ln of a quotient, the difference of the logarithms is ln of a quotient. And then the sum of the logs is log of the product. Interestingly enough, this factors, right? I mean, perhaps you had seen that already. Why don't we take this time to simplify as much as possible? This factors as x minus 2, x minus 3. So we can cancel one of these, and we can cancel one of these, leaving us with log of x minus 2 squared times x minus 3. How are we doing here? Questions? All right, so perhaps a good place to end then. I will invite you to work out some problems as soon as possible. Get a mastery of this material, exponentials, logarithms. How do we know if we should multiply to the top or to the bottom? Multiplication is to the top, right? Multiplication is to the top. Can you still break down? How someone was asking for a single logarithm, right? So we just have that single log. I think that's the way to go. Did you? I mean, if you're thinking of expanding, it's fine. You could. It wouldn't make it any simpler, though. I think this is what they were looking for. Yeah, exactly. All right. So a good place to end. I'll see you guys on Friday. Thank you all for coming. First graded web work, I will probably open up next week. No, in fact, I will open it up next week for sure. Possibly Monday, but we'll see. I'll announce it. You have WebWorks, a midterm, and a final exam. Same time on Friday, absolutely. The first WebWork is not graded, but I think there is an issue. And by first WebWork, I mean WebWork 0 or orientation, depending on how it's called. It's not for Mark, so don't worry about it, but there seems to be a confusion with that new WebWork system, so we'll be, I'm working it out. Page numbers for the 8th edition. I want to say we're still on section 1.5. Look, I mean, what are we doing? If you're using a different book or different edition and it's on the same page, we're doing logarithms. So figure out in the book you're using where logarithms occur, where logarithms are defined for the first time. It's usually going to be the section after exponentials. So do some exercises from logarithms. There's still a bit for us to do here in the logarithm section. So, you know, I mean, don't go too far. Don't really go past 46. I mean, unless you have seen exponentials and logarithms before and you're very good at them, you can try your hand at questions following those. Otherwise, we'll do a few more on Friday. So I'll see you guys then. Have a good one.